since someone's going to ask, no, not a shop injury, just a disagreement with a friend's cat. I wanted to give him scritches, he was very strongly opposed to that idea, so we reached a compromise wherein he got everything he wanted. Hello Internet, my name is Quinn, and this is Blondihacks. I'm working on my DC generator project today. We're going to make the end bells, which are surprisingly intricate little castings, and there's quite a few unexpectedly, let's say challenging operations in this one. So let's go. When last we left our generator, we had the base casting mostly done. Now it's time to move on to the end bells. End bells are these two cute little aluminum castings. They've got these kind of spokes on them, and they are supposed to fit on there like that. Man, they don't fit at all. That's odd. Ooh, I know. Let's try machining them. That might work. This is the fancier of the two bells. There's a 4-bolt pattern around the outside, and then there's these 2 pads in the middle, which are for the electrical binding posts. Then, of course, we'll have to do the main rotor bore through the center. On the back, we need to create a flat flange here, and then there's a little ridge that registers on the inside of the bore of the main casting. So lots of stuff to do. I'm going to start on the lathe. I'm going to need to hold it in the lathe, something like this, in order to do the flange on the bottom. The first thought that occurred to me is maybe it'll fit in the forejaw, and this is seriously tempting because by remarkable coincidence, the forejaw jaws on my forejaw chuck are an exactly perfect fit in those spoke openings. That just seems crazy enough to work. Getting it aligned will be tricky. It wants to move around a bit because those are rough cast surfaces, but this feels sufficiently plausible that I'm going to set it up on the lathe and give it a whirl. I'll snug it up all the way around. It's certainly secure in there. It's not going to go anywhere. The only question is, can it be dialed in, or is it sufficiently concentric as is, perhaps? Get an indicator on it and find out. The answer is, off the bat, no, it is not sufficiently concentric. There's quite a bit of run out in that. So I spent some time trying to dial it in, but you've probably already figured out why this isn't going to work. You can't dial something in a forejaw unless the part can move independently on each axis of the other 2 jaws. And in this case, it can't. So there's no way to dial it in because the part can't slide in the 2 opposite jaws from the ones you're adjusting. It's locked in on all 4 sides. So I spun it up anyway just to see how bad it is, and yeah, it's really bad. This isn't going to work. Plan B then, I found this piece of scrap, and I'm going to try and make a mandrel out of it to fixture this guy. It looks like I should be able to use some small bolts with washers on them and kind of clamp the spokes of the end bell to the surface of this mandrel. I think that might be crazy enough to work. I'll center it roughly by eye. It doesn't really matter because we're going to dial it in anyway. And I'll center punch a position for 1 bolt that's right next to the spokes on one side. That seems like it'll work. So I'll drill and tap that one first, and then I'll be able to do the other one on the opposite side once I know where the first one is going to land. I'm going to line that up with the center drill on the mill, and I'm going to center drill, and tap that for the bolt. Now I can fish that in there with the first bolt roughly installed, and then I can transfer punch a position for the second bolt right next to the hub. This scheme only works if the bolts are basically touching the hub on either side, very, very close. Otherwise, the piece might be able to fly off if it can escape past the bolts. So the other one was drilled and tapped, and quick test fit. That looks very secure indeed. I do believe this will work. If you are really worried about it, you could do 4 bolts, but really 2 is plenty. That is going to hold no problem on there. Over to the lathe then, and now to dial it in. It should be pretty straightforward because, of course, the mandrel is being held by the forejaw, and we're going to dial in the casting, and the mandrel can move freely as needed within the forejaw. Dialing in a rough casting is always a little bit of a fool's errand. All you can do is try to visually average out the noise in the surface texture and the out of roundness of the casting. There's always going to be some, but I think I got it to within 5 thousandths, which is pretty good for a casting. These PM Research castings are consistently very good in my experience. And that looks quite good indeed. I think that'll be just fine for what we're doing. Next then is to face down this flange area. The drawing conveniently gives us a measurement for the thickness of this flange, but of course the thickness is measured against the back side of the flange, which is a rough casting, and so this dimension is always going to be approximate. I took measurements at a few points all the way around the flange and just kind of averaged them. This dimension is not too critical. There's no tight tolerance or anything on the thickness of this flange. A couple more passes after that initial cleanup cut should do the trick. I'm taking fairly light cuts here because I'm not sure exactly how rigid this setup is. The machining forces are being resisted by those cast aluminum spokes, and they are pretty spindly, so I don't want to push my luck too hard here. I could imagine this casting cracking, and also we're probably going to run out of rigidity at some point because those spokes probably aren't very rigid, but this seemed to be working just fine. I was getting really nice cuts. Once I was happy with the average measurement all the way around being basically what the drawing says it's supposed to be, then I could go on to creating the registration diameter that sits just inside the base casting and keeps the end bell centered on the casting. This is a very important diameter because it's also going to be centering the rotor ultimately. So this needs to be a very accurate dimension. However, this flange is very, very shallow, so I have to use the guessimeters to measure it. There isn't enough thickness on this flange to get a micrometer in there. However, the guessimeters are not precise enough for the kind of fit that we need. I'm looking for like a 1/2 thou slip fit. So the way I handle a situation like this is to get close with the guessimeters and then just do a lot of light cutting and test fitting. Once you're, say, within 5/1000ths of the final dimension, then I just start taking 1 thou and 1/2 thou cuts and test fitting after each one. With experience, you get to the point where you can feel when two pieces are almost fitting together. So you know when you're close, and then when you're close, you just start taking very, very light cuts. As long as you're only taking a 1 thou or a 1/2 thou cut, then you'll be within a 1/2 thou of your final dimension, guaranteed. And just keep doing that until the fit is perfect. Oof, look at that. Let's look at that from another angle because it's so awesome. Fits like that are why machining never gets old. That could not be better, honestly. Here's the other end bell. It's much simpler. As you can see, it doesn't have that deep dish. But I should be able to use this same setup, I think, to machine this fellow. Let's give it a shot. I'll pull the other casting off, and then I'll fish the other bolt in on the side of this new casting. Then I line up the other bolt and fish that one in. Just gotta line that up. Just line that up and line that up and fish that in there. Just gotta line that up and fish that. Yeah, maybe I'll loosen the other one a little bit. Yeah, that'll help me get the two aligned. I'll line that up and yeah, this isn't going to work. Maddeningly, this other casting has a hub that's ever so slightly larger, so I had to drill 2 new holes over on the mill to make room for this casting. I suppose I could have filed a little bit off of the hub on this casting, but I didn't feel good about doing that. This casting was dialed in and machined just like the other one. Over to the mill now. I thought I could probably use this same fixture to do some features on the other side on the mill. I'll pull this casting off, and I think I can just flip it over and bolt it down this way and do the bolt pattern. It looks like the bolts will kind of hold with the washers at a cattywampus angle. It's a little awkward, but it actually seems secure, so I think this will be fine. I wouldn't trust this setup for some heavy milling, but for drilling tiny holes, it's fine, I think. For the bolt circle, I could of course use the bolt circle function on the DRO, which would be very tempting. However, this is a 4-hole pattern, which means literally the 4 bolt positions are just plus and minus the radius of the bolt circle on X and Y. Plus and minus the same value on both axes gives you your 4 holes, and that's a whole lot easier. What I did then was put a gauge pin the same size as the bosses in which I need to center the bolt circle, and I lined up that pin on one of the bosses, then iterated through my bolt pattern and checked that the alignment was as good as possible on all 4 bosses. And of course it isn't the first try, so then you adjust the center position on the DRO a little bit and try again. And you just keep shuffling the center position around a little bit until you get a position where the DRO's center is in such a place that all 4 holes land centered on their respective bosses. It's a little bit of trial and error, but it takes longer to explain than to do it, honestly. Then all 4 of those holes were center drilled and drilled. In a case like this, all 4 of them are never going to be perfect. No casting is so perfect that you can get all 4 of the holes perfectly centered and land on the correct spacing, but those worked out pretty good. I also considered spot facing these, which is often done with bolts clamping against cast surfaces. The drawing does not call for that, and there really isn't enough material here to do that, and the bolts look like they're going to be just fine as is, so I decided to leave that alone. I tried bringing in the other end bell now and doing the same thing. However, there was really no way to clamp this one this way around with this mandrel fixture thing. Even with longer bolts, it wasn't going to work in such a way that I had access to these extra little pads that are for the electrical posts. I need to do all 6 of these bosses in this setup, so I have to do something different. Instead, I brought in my fixture plate and I got some parallel-sided scrap, and I'll clamp the piece down to this, and that'll be sacrificial underneath for drilling the holes, and I'll strap clamp it down by the spokes. That gives me access to all 6 of the drill bosses in a way that the clamps are not interfering. Same procedure here, line up the pins, figure out the bolt pattern, center drill, etc. Next up though, I can do the 2 electrical post bosses in this same setup. These do need to be spot faced per the drawing so that the binding posts have a nice square surface to clamp on. So I started by doing that operation. Just came in with a small end mill and faced down what looked like an appropriate amount off of each boss. Now to line up the hole pattern here, the drawing gives the spacing between the 2 posts, and of course we want those posts to be reasonably centered on their respective bosses. So once again I come in with the gauge pin the same diameter as the boss. Since these 2 bolts are at a 45-degree angle from the bolt pattern in the flange, then the distance between these 2 holes forms the hypotenuse of an isosceles right triangle. So I can easily calculate with a little bit of trig what the delta x and y should be between these 2 bosses. So then I go back and forth once again, fine-tuning the position of the pattern until the same delta on x and y gets me centered on both bosses. Then I know I'm at the correct angle for the 2 holes and they're the correct distance apart. And then once again, center drill and drill. As you might expect then, I tore down the setup and started deburring both sides of all those holes. While I was doing that though, on the inside of the larger end bell, I noticed something a little odd. Where the binding posts go through on the back, there's really nowhere for them to clamp because the holes come through the angled casting area in kind of a funny spot. Something didn't seem right there, so I went and checked the drawing, and it turns out I had missed an operation on the inside of this. We're supposed to do a large counter bore in here to square up the inside of this bell. Now, it's just as well I wouldn't have been able to do it in that setup that I had anyway because the bolt heads would have been in the way, so I need to do a new setup in any case. I grabbed this large piece of round bar off the stockpile, and I'm going to find an approximate center of it with my center finder, and then I'm going to put a nice, generous 60-degree center in the middle of this thing. You'll see why in a moment. Then centered on that center drill, I'm going to do the same bolt pattern, same bolt circle as is in the flange. And what I'm going to do is I'm going to create a big dish shape in this fixture that's going to allow me to clamp the end bell upside down up against the back side of the flange. In other words, I need to do a large counter bore that's big enough to fit the entire end bell. So I'll do that on the lathe. Job 1 then is to get that center mark that we made centered in the lathe. To do that, I'll bring in my dead center and suspend it between the center mark and my live center. This is a great trick for getting any center or punch mark centered on the axis of your lathe. With the dead center now suspended, I can then dial in the dead center as though it was a piece of stock. I find this technique to be extremely accurate and much quicker and easier than a lot of the other methods people use for doing this. Quick ichrometer check, and you can see that that center drill lives up to its name. It is indeed very well centered. Alright, now I can start hogging out material for this large counter bore. I'm going to drill out as much as I can to save us a bunch of boring bar time. I started with my largest standard twist drill, and from here I'm going to move up to increasingly large and maniacal drills because thanks to a viewer I now have a pretty complete set of Silver and Deming drills, which is an old-timey name for reduced shank drills. You got to be a little careful with these things because they can easily overwhelm the rating of your Jacobs check. If your Jacobs check has a 1/2 inch size limit, then it's engineered to clamp on something that can apply the amount of torque that can be applied by a 1/2 inch thing. When you start putting in larger things like Silver and Deming drills, they can put a lot more torque on that shank than the Jacobs chuck is designed for. But if you go easy, don't ask too much of them. This is just aluminum and I'm taking moderate cuts with them. It's just fine. I ran out of drills, so it's time to move on. Before I do the boring, I'm going to face this just to make sure that we've got a nice square clamping surface. I took a couple of cuts on it. I didn't clean it up all the way. There's a little bit of an old saw cut there, but there's no point in facing all the way down to that. It's just going to waste material. All I really need is the clamping flange area to be square. Now I can come in with the boring bar and open this up all the way to the size needed to fit that end bell. After a few passes though, I felt like something wasn't right. I was getting pretty close to my bolt circle, but I still had quite a ways to go according to my measurements before the end bell was going to fit inside here. This hurt my brain a little bit for a minute. I wasn't sure what was wrong here. Then I took a closer look at this casting, and in fact, you can see that the base of the angled spokes is larger than the inside of the bolt circle. So if I create a counterbore large enough for those spokes, I'm going to eat up my bolt holes. There's a couple of things I could do at this point. One would be to take this out, go over to the mill, and plunge an end mill down in a pattern to create slots for these spokes to fit in so that I don't have to enlarge the counterbore in the area where the bolt holes are. However, I've got a perfectly concentric setup right now that I don't want to lose. Another option then would be from this same setup, cut some keyways in there for those spokes using the lathe itself. I did a whole video on cutting keyways with the lathe. You can do it, of course. However, that would be quite a bit of work. These are deep and wide spokes, and cutting keyways with the lathe while possible is not fast. So instead, I'm going to use a little more of a farmer solution. I can put some stacks of washers in here and space the flange off of that surface, as long as I can come up with 4 stacks of washers that are close in dimension, which actually isn't as hard as it sounds. If you've got a bunch of washers that were all bought at the same time from the same package, they were probably made at the same time, they were stamped from the same sheet of material, they're going to be extremely close in thickness, and you can pretty easily come up with a stack of them that's within a couple thousandths of another stack. I could also, of course, go and machine some really accurate spacers for this, but those spacers are going to be sitting on the back of the flange, which is, remember, still rough cast, so it's not going to be a very accurate setup anyway, and the counterbore feature that we're doing inside here doesn't need to be that accurate. All we're doing is creating clearance for the rotor and a flat spot for the back of those binding posts. With my stacks of washers clamped in there, let's see how this thing runs. And well, not great. Doesn't look too good. There's a lot of run out on that face. Let's get an indicator and find out how much. Looks like it's about 25 thousandths. Now, I said this feature doesn't need to be that accurate, but I think I'd like to do a little better than that. The worst case scenario would be if this bore is really crooked, then the spokes could get cut too thin in one area or another. But we can easily fix this without getting too crazy. I found the low spot, and I cut a little U-shaped 10 thou shim from shim stock, and I slid that in underneath the lowest of the stacks of washers, tighten that back down, take another reading, and now we are 15 thou out. So we made it 10 thou better, as expected from the 10 thou shim. So I did one more 10 thou shim on that same low spot, and I did about an 8 thou shim on one of the adjacent posts, and now the whole stack is within 5, maybe 6 thousandths. I think that's good enough for this. We'll do a quick ichrometer check on that, and that looks good enough. If you're wondering why that wasn't better, I think it's a combination of the back of the casting being rough against those washers, and also when you compress those stacks of washers, their dimensions change a little bit because the washers have burrs on them and stuff for manufacture. These washers are going to be in the way of the cut somewhat, so I did my best to kind of push them out of the way, but they are a little bit too large for what I need. Honestly, any kind of post that I made to fill in these gaps would have to be very, very thin in order to not get in the way of the boring bar, so these washers are going to be sacrificial, as would probably anything that we did in there. The drawing gives a distance for the depth of this counterbore from the flange, so I touched the boring bar off on that, and away we go. The cut starts off very nice. Once inside the rim, the sound changes to more of a staccato sound, which is of course cutting the spokes, combined with the dulcet rhythms of washers giving up their lives for the cause. That first cut seemed to go fine though. Let's stop and take a look at what's happening. Oh yeah, that's cutting beautifully. And yeah, we're definitely machining those washers away, but that's okay. Washers are cheap. Let's take a quick measurement and see how much more I have to do. Probably just one more cut. Quick check, and yeah, we are within finishing cut range. This cast aluminum is machining really beautifully, I have to say. I did also need to add some depth to the entire counterbore across the back, which you can't really do with a boring bar. There are special boring bars that are designed to plunge. This is not one of them, but you can kind of get away with it if you just do some light cuts. So what I did is I just nibbled away at the center area there until I had enough depth in the center that I could then feed in and then feed across to face the back to the correct depth. This being aluminum, you can get away with that kind of stuff. I probably could not have done that in steel. That cut came out great though. You can see the binding posts have nice flat clamping areas there now. The spokes are squared up on the inside. There's one area that didn't clean up on the casting. That's probably a little bit of misalignment on the bore feature. Could be an imperfection in the casting. It could be an accumulation of errors from all my previous setups, but regardless, it's harmless here. All right, break down that setup, and this piece is looking pretty neat. I like this thing actually. It's got a real kind of machiny, sort of almost spacey kind of look to it. It's quite a complex shape. These washers took one for the team, but honestly, there's only a few of them that had too much material removed to where I would feel good about using them as washers. The rest of them went back in the box. The next thing to do is to get the threaded hole pattern on the base casting in order to mount these end bells. I decided to do this by transferring these holes rather than relying on the bolt circle function or other methods to do this directly in the mill, because I want to guarantee that these end bells land nicely lined up visually. I want those spokes to be horizontal and vertical respectively. So I'm going to line it up visually, and I'm going to measure square from the base of the bottom casting there to make sure that the spokes are sitting nice and horizontal across the middle so that it'll look nice when it's bolted in place. Once I'm happy with that alignment, then I transfer punch the first hole in that position. I can then deepen that punch mark and line up my spindle pointer on that punch mark and drill and tap the first hole, and then I will install the end bell, bolt it down with this first hole in order to transfer the rest of them. The reason that I'm doing it this way is that even though on the milling machine it would be quite easy to create a perfect 4-bolt circle that's perfectly square to the bottom surface of this casting and perfectly centered on that bore, it still might not line up with the holes in the end bell, or the end bell might bolt on, but it might be a little crooked. And the reason for that is that, remember, that bolt pattern was aligned with those bosses, and even though the diameter of the bolt circle is correct, the orientation of those holes relative to the casting is not guaranteed because that was done by eye. To transfer the other 3 holes, I line up the clearance drill that was used to drill those holes in the end bell, and then I drill into the material below that hole just a little bit. And what that does is it creates a dimple that's centered in that clearance hole. So now I can come in with the tapping drill size, which is smaller than the clearance hole, of course, and it's going to center itself in that clearance hole. This is a really easy way to get a tap drill centered perfectly on an existing clearance hole. If you just go straight in with the tap drill, it might wander off and it'll catch on the sides of the clearance hole, but it won't be centered in that clearance hole. And often you can get away with that, but if you're trying to make a really perfectly aligned bolt circle, then this clearance drill dimple technique guarantees it. And as a nice side benefit, it creates pre-chamfers, if you will, on the holes, so you don't have to chamfer the holes when you're done threading. Now, if I did my job right, this end bell should bolt on easily because all 4 holes perfectly align up, and the spokes of this end bell should be perfectly horizontal and vertically by eye, and thus look nice. And that looks very nice indeed. I'm very pleased with that. So the end bell on the other end was then done the same way, exactly as you just saw, and now it's really starting to look like a generator. The trickiest operation though now is we have to get a bore all the way through the center of both of those castings, and those 2 bores have to be perfectly aligned so that the rotor will run smoothly inside this casting. This is the setup I came up with to hopefully do that. I'm going to clamp the whole assembly to a 1-2-3 block, which is basically acting like an angle block. I'm going to bolt this down to my mill table using a threaded rod through the center, and that's going to hold this thing perfectly square to the bore on the x-axis of the mill. Then I run an indicator down in the bore to line up the casting on the y-axis of the mill. So now the casting should be sitting perfectly straight on the mill. So now I just need to get a bore drilled through the center of both castings. I know that bore will be square so that the rotor that's going to be running in bearings in that bore is going to be straight and square. However, aesthetically now I want to try and get the bearing holes lined up with the centers of the bosses on the end bells. So I brought in a piece of stock that's the same diameter, and I lined it up with the top boss. Then I remove that end bell and I line it up with the bottom end bell boss by looking at it from behind. And then I once again have to kind of compromise, just like the bolt circles, because the castings aren't going to be the same and they weren't both machined perfectly the same. So there isn't going to be a position where both bosses are perfectly centered. So you just have to go back and forth and split the difference on error and try to get both of them as well centered as you can. Another way to do this would have been to put the whole assembly on the surface plate and do casting layout to find a center on the bosses at both sides that was well aligned, but this worked fine for me. Quick prayer to Metallic Ore, the god of machining, and away we go. I've center drilled that, and now I'm pilot drilling for the reamer, and the pilot drill is going to go through both bores. My idea is that doing both end bells in a single setup like this should guarantee the alignment of these two bores. That's why I didn't do them until now. I could have done them in many of the previous setups that we did, but by doing them all at once at the end like this should guarantee their alignment. So once the pilot drill has gone all the way through, then I come in with a reamer and I ream them to final dimension. This has to be an accurate dimension because the bearings are press fit into these bores, so the dimension of this bore is just as critical as the alignment of it is. Quick sanity check with a drill the same size as the bore, and that runs smoothly in there once it's lined up with both bores, so that's a good sign. Now let's check the dimension of this because it's, once again, a press fit. Dimension is really critical. A 250 gauge pin slides in there just barely, but it does go in. That's the nominal dimension. Now 251, 251 does not go in, so that's good news. That means we're dead nuts. We're somewhere between 250 and 251. Which is worth metric horns of victory. If you wanted to know exactly what that bore is, you can get higher resolution gauge pins, but this resolution is sufficient. Moment of truth though, how well centered is it on the other end bell, which I couldn't really see? And the answer is, hey, not bad. Actually, I think the far one is better centered than the near one, so yeah, I'll take that win. I punched registration marks on the bottoms of both end bells to make sure that they both go back on the same sides and the same orientations as they are currently. In a perfect world, you could put them back on in any old way and everything would still line up. I don't think that's probably true though, considering how much match drilling and fudging and so on that I've done. So, here in the hobby shop, just punch everything so it all goes back the same way. Time to install the bearings now. As you can see, they don't fit yet because they are an interference fit, and quite an aggressive one. These are actually almost a 2.5 thou interference fit, which is very aggressive, especially for parts this small. And that's quite aggressive for a cast part. Castings don't like aggressive press fits. They do have a tendency to crack. So I'm not crazy about trying to press that in. I have seen much larger castings than this crack under an overly aggressive press fit. Instead, I am going to try a shrink fit. I happen to have a toaster oven in my shop now, which is a useful thing, and I'm going to try and heat these things up. According to one of those online thermal expansion calculators for aluminum, 250 degrees should be enough to expand them by 3 thousandths, which should cause those bearings to just drop right in. So I heated these up to 250 degrees, and let's give it a whirl. Survey says, nope, not even close. So I put it back in, and I cranked it up to 375. And still, nope. So I put it back in, and I cranked it up to 450. And since someone's going to say it, yes, you can also put the bearings in the freezer, but honestly, I think that's a little bit of a myth. If you do the thermal expansion calculations for press fits, you usually need somewhere in the range of 200 to 500 degrees of temperature delta, which is easy to do in an oven. Putting bearings in a household freezer is only giving you like 80, 90, 100 degrees at the most temperature delta, which is not enough to make any difference, especially with steel. With aluminum, maybe, because aluminum expands a lot, but if you're going to use cold, you have to use liquid nitrogen, or I think you're wasting your time. I suspect the reason that myth persists is because people do it with roller bearings, which typically have very, very light interference fits. In fact, they're typically locational transition fits, which is a couple of tenths of interference at most. And yeah, you can get that out of a household freezer. In this case, 450 was still not enough to get those bearings to drop in. So, plan B, I moved my press over close to the oven, and I took them out of the oven while hot, and I pressed them in. The heat expansion has still helped a lot. It has made this into a very, very light press fit. So I wasn't worried about cracking the castings doing that. And this actually worked super well. After each one, I put it back in the oven, and I'm going to leave them in the oven and shut the oven off and let it cool down slowly just to avoid stressing these castings. Once everything had cooled down, I should be able to test fit the rotor. The rotor comes with the kit all assembled. Quite a nice little piece. It's just a standard DC motor rotor. I don't think there's anything special about it, but it's nicely made. That slides into one end bell like so, and then the other end bell should bolt right on. All right, moment of truth. Feels pretty good. Give it a spin. Oh, look at that. Oh, that spins so nicely. Oh, that, kids, is why a machine shop is the finest of hobbies. It just does not get better than that. It's perfectly silent and smooth, and it'll spin for days, just like it should. Wow, that really could not have gone better. I left this much end float in it. A bushing motor like this, or a bushing generator in this case, is supposed to have some end float in it. It relies on the magnetic field to self-center it. The rotor should not be touching the bearings at each end when spinning. Well, that has all gone pretty well so far. I'm pretty pleased with progress. Got a little ways to go before we're making volts, but it's really starting to look and feel like a generator. I hope you've enjoyed this process so far, and I hope you'll keep watching for the rest of this series. It's going to get pretty neat. Trust me, you're going to want to stay for the end of this one. Thank you very much for watching, and thanks so much to my patrons for making all of this content possible, and I will see you next time.